So folks, now that we've learned how to take the determinant of a 2x2 matrix, let's move on to higher square matrices. So let's look at this 3x3 determinant, or sorry, this 3x3 matrix, and let's compute its determinant. So here's a formula for computing the determinant. If these are the entries A through I, the formula for computing the determinant is AEI plus BFG plus CDH minus CEG minus BDI minus AFH. So there is a formula for the 3x3 determinant. I don't think it's worth learning this formula or even looking it up, but there it is. We've got a 3x3 formula. Instead, we're going to compute the determinants through a process called expansion by minors, which we'll see on the next page. So I think all instructors would agree it's not a good idea to just memorize this formula, although this is handy if you were to be writing a program to compute the determinant. That might be helpful. There is a shortcut for computing a 3x3 determinant, separate from what I'm going to show you. And this shortcut is especially helpful for, say, Calculus 3 or for physics courses when you're restricted to 3 dimensions. However, I don't teach this method because we're going to do determinants of higher matrices, higher order matrices like 4x4s potentially, or maybe even higher. And the technique that you learn, the shortcut technique for a 3x3, doesn't extend. But if you like, I've included a video here which teaches that shortcut method for computing a 3x3 determinant. And I would say that if you're in a physics class, that you might find this formula helpful. Instead, we're going to find the determinant of any n by n matrix other than 2x2 through a process called expansion by minors. And I'll talk more about this process a little more formally in class, but let's just put it into practice. So what we're going to do here is compute this 3x3 determinant. And I'm not going to, there's actually maybe a faster way that I'm about to compute this, but I'm going to go ahead and what I'd like to say is I'm going to expand down this column right here. And you'll see what I mean as we write through this. So in the process of expansion by minors, what we can say is that for this matrix, and we're trying to compute its determinant, that we pick a row or a column to expand down, and we'll talk about this more in subsequent examples about how the signs work. But for right now, I'm going to write out 5, and then we will go ahead and expand. The way I want you to think about this is I'm going to, for the value 5, I'm going to think about blocking out this column and blocking out this row, and notice that I'm left with a 2x2 matrix. And so I'm going to then compute the determinant of that minor 2x2 matrix. Okay. Then I'm going to pick the, I'm expanding down this column, so now I'm going to go to this entry right here, and I'm going to think about blocking out this column and this row, and then notice that I'm left with 4 entries that aren't blocked off, and I'm going to compute the determinant of that remaining 2x2 matrix there. The next thing, though, the next thing to see is that we would write minus 4, where this sign here is a positive 4, and we're going to put a minus 4 here. We'll talk about that in the next example. But then if we look at the remaining 2x2 matrix, we have minus 2, minus 3, minus 1, and 2. And then for my final entry, because I'm expanding down this column here, the final entry is this 4 here. So I'm going to think about blocking out this row and this column, and that's going to leave me with this remaining 2x2 matrix right here. Hopefully you can envision that. And so we would have a plus 4 determinant bar, and then negative 2, negative 3, 0, and 1. Okay. So in this case, one thing that maybe you have questions about are signs alternated as positive, negative, and then again positive. And we will talk about that in the next example. So if you have questions on that, that's actually a good thing. But then what you can see is we took each entry and we thought about, in the case of our first entry here, we thought about blocking out this row, this column, and that left me with these remaining entries, which form a 2 by 2 matrix, and I'm computing the determinant of that remaining 2 by 2 matrix. So this is what we mean. This is a minor matrix sitting inside of the larger matrix, and that's what we mean when we say this process is called expansion by minors. So let's go ahead and compute. We know how to compute the determinant of a 2 by 2 matrix based on what we did in our previous video. So we take 0 times 2, and then minus from the formula, and then 1 times negative 1. Likewise, we'll have negative 4, and then we'll compute the determinant of this green, this second 2 by 2 matrix. And if we compute that, we have minus 2 times 2, minus from the formula, negative 3 times negative 1. And we have, for the last entry, plus 4 times times the determinant of this remaining orange 2 by 2 matrix. So we would compute that using the formula, and we'd have negative 2 times 1 minus negative 3 times 0. In continuing that computation, we get, in this case, 5 times that entry 0. This entry would be a positive 1. So that determinant of this red 2 by 2 matrix is 1. Minus 4 times, here we would have negative 4 minus 3. So that gives me negative 7. That is the determinant of this green 2 by 2 matrix was negative 7. And then plus 4 times, and here we would end up with negative 2. That is the determinant of this orange 2 by 2 matrix came out to be negative 2. And if I clean all this up, we've got 5 plus 28 minus 8. And so the determinant of this 3 by 3 matrix is 25. Again, folks, at this point, I'm not giving you much of an insight as to what we mean by the determinant of a matrix, other than at this point you should know that it's a number that somehow encodes some information about that matrix. And we will talk more about that as we go further along. So this example was meant to illustrate this process called expansion by minors. And I think that the process is relatively straightforward except for the issue of the signs. And so I want to talk about that here. And my mouse is not cooperating. Or the mouse is cooperating, OneNote is not. All right, here we go. So what we're going to do is let's go ahead and look at some matrices of signs. We'll do A1, A2, and A3. There are 2 by 2, 3 by 3, 4 by 4 matrices whose entries, whose ijth entry is the sign of the expression negative 1 I plus j. So we're only going to formally write out a sub 1. And this matrix, we said that the first entry, the 1, 1 entry, would be negative 1 to the, since it's the 1, 1 entry, it'd be 1 plus 1, because I is our, when we list I first, that makes it our row. We're in the first row, first column. And for the next entry, we'd have negative 1. We're still in the first row, but now we're in the second column. So that would be that entry. The next entry down would be negative 1 to the, and then we're in the second row, first column. And the final entry is the 2, 2 entry. We're in the second row, second column. And so if we do this computation, we get 1, negative 1, negative 1, 1. And I should be a little bit more careful here. I said that it was the sign of that expression. So bear with me here. This is not actually our A. This would just be some other matrix. Maybe we call it B1. And so our A1 is the sign of each one of those expressions. And the sign on this first entry is positive. The sign on this second entry is negative. The sign on this entry right here is negative. And the sign on this entry right here is positive. So we could do the same thing. We could compute, maybe B2, and I'll just start writing out B2. It's a 3 by 3 matrix, and it would be negative 1. It's the first row, first column, so that's 1 plus 1. And it's the first row, second column. And then for this entry, we'd have the first row, third column. And we could fill out the remaining entries, we've got several more to go, we could fill out those remaining entries. Then, to state what A2 is, we would go ahead and just look at the sign on each of those entries. Well, notice that this is -1 squared, which is going to have a positive sign, so we put a plus sign there. This is -1 to the third power, which is going to have a minus sign. And this is -1 to the fourth power, which is going to get a positive sign. And if you were to fill this out, you see that it has a nice little pattern. So we call this thing the matrix of signs. And so let's go ahead and we'll actually just compute A4 without actually resorting to the computations, because we notice a pattern. Every entry that's in a odd position or an even position, as far as what do I mean by that? We're in the 1, 1 entry. If you sum those together, you get 2. Here is the one, let's say it like this. If you're in the 1, 2 entry, you sum those together, you get 3. So if the sum comes out to be even, you'll get a plus sign, and if the sum comes out to be odd, you'll get a minus. So a consequence of this is that the signs just alternate, and notice that next to any positive sign, the 4 entries nearest it, above, below, left, and right, all have opposite signs. And so that makes it very easy to give these sign matrices. Why did we need this information? Well, we'll talk about that on the next page, but notice that if I were to go back to this 3x3 matrix where we computed the determinant through this process of expansion by minors, the confusing thing was deciding the sign. But if we looked at its corresponding sign matrix, this is its corresponding, and I guess it's a matrix, this is its corresponding sign matrix, and this entry here, then the 1, 1 entry should have a plus sign in front of it. And this entry here, in this case we are the 2, 1 entry, and it should have a minus sign on it, and this sign got a plus sign. Notice that all 3 of these signs, the plus, the minus, and the plus, are independent. They have nothing to do with the signs on the entries of the matrix themselves. So if this had been a minus sign, I would have a -4 here, for instance. So folks, that's been a long video. That's a good place to stop. So we'll pick that up in the next video, where we find the determinant of higher ordered matrices, a 4x4, for example.